In this video we're gonna talk about uniform continuity. So, given a function f that is defined in an interval, we say that f is uniformly continuous in the interval a. If given an epsilon that's greater to 0, we can find a delta greater to 0 with the property that if x and x prime verify that the distance between them is smaller to delta, then the absolute value between f of x minus f of x prime is smaller to epsilon. This definition is extremely similar to the one about continuity, but there is a very small difference that will be clear for you in the examples. But the difference between ordinary and uniform continuity, it's very subtle. The difference is only delta we find. In ordinary continuity, the delta we find depends both on epsilon and on x. But in the uniform continuity, the delta depends only in epsilon. So here delta does not depend on x. And the difference is in the way we write this definition. Here we have that there exists a delta with the property that if x and x prime verify this, then this other thing happens. But in ordinary continuity, the order in which we wrote stuff is what gives us this delta that depends on x. So let's visualize this with an example. So we want to prove that f of x, defined as x squared, is uniformly continuous in 1, 2. So to start this, we have to take x and x prime, two numbers in the interval 1, 2. And let's first calculate what the function minus the function in x prime gives us. Using the definition of the function f of x is x squared, we have that this is the absolute value of x squared minus x prime squared. Now we can rewrite this as x minus x prime times x plus x prime. And now, because the absolute value of the product is the product of the absolute values, this is the absolute value of x minus x prime times the absolute value of x plus x prime. But now both x and x prime are in this interval, so they are both smaller to 2. So we can bound this sum and say that this will be smaller to the first term, we just leave it as it is, times, and instead of writing x, we write 2, plus, and again, instead of writing x prime, because it is also in this interval, we write 2. And this is 4 times x minus x prime. So now, we let epsilon be a number greater to 0. And we are going to take delta to be epsilon divided by 4. So then, if x minus x prime is smaller to delta, then f of x minus f of x prime, we said that this one was smaller to 4 times x minus x prime. But now this is smaller to delta, so this is smaller to 4 times delta, and we just took delta to be epsilon divided by 4. So this is equal to 4 times epsilon over 4, which is equal to epsilon. To sum up, we took an epsilon greater to 0, and we were able to find this delta such that if x minus x prime was smaller to delta, then f of x minus f of x prime is smaller to epsilon. But now the important thing here is that delta was equal to epsilon over 4, so it doesn't depend on x. So then we know that f of x equal to x squared is uniformly continuous. Now, something important that we get from this is that if f is uniformly continuous, then f is continuous. What I'm saying is, we have, let's say we find a delta that doesn't depend on x. Well, for f to be continuous in the ordinary sense, we don't necessarily have to have this x here. If delta depends on epsilon, the function will be in particular continuous. But does it work the same the other way around? Is every continuous function uniformly continuous? To see this, let's first think of the negation of uniformly continuous. So, if f if a function is not uniformly continuous, then we have to negate that first definition given in the video. So the negation of a for every epsilon greater to 0 is an existence operator, so there exists an epsilon greater to 0, such that we have to now negate the existence of the delta, and that is for every delta operator greater to 0, there exists x and x prime in the interval a that verify that x minus x prime is smaller to delta, but f of x minus f of x prime is greater to epsilon. This is the negation of the conclusion we had in the definition. So whenever we have a function that we want to prove that is not uniformly continuous, this is the definition we want to use. So let's go ahead and use this in an example. Now we have f that is defined in the set 0, 1 open to the set of the real numbers. And f of x is going to be 1 over x. So we know that f is continuous, because f is a rational function, and we saw in a previous video that rational functions were continuous. In this case, 0, 1 will be our interval a. So now we have to let delta be a number greater to 0. What this let delta greater to 0 is telling us, it is marking this for every delta greater to 0. Because we're not taking just a particular delta, we're just letting delta be a number that's greater to 0. So now we're gonna take epsilon to be equal to 1. And now we are actually taking a particular epsilon, and that is because we have the existence for the epsilon. And we want to prove that the function is not uniformly continuous, so this is the definition we're using. So, given x and x prime that are in our interval 0, 1, and such that x minus x prime is smaller to delta, we want to show that f of x minus f of x prime is greater than or equal to epsilon. Again, this greater than or equal to comes from here in the definition of the negation of uniformly continuous. Now what we're going to do is, we're going to take a natural number n such that 1 over 2n is smaller to delta. This number obviously exists because delta is a positive number. And now we're gonna call x 1 over n and x prime 1 over 2n. This is something, again, we have to do because there exists x and x prime, so we have to actually find them. So we took x and x prime to be these two numbers. It's obvious that x and x prime are in the interval 0, 1. X minus x prime is the absolute value of 1 over n minus 1 over 2n. this is the absolute value of 1 over 2n, and because n is a natural number, this is a positive number, and it is 1 over 2n. And we took 1 over 2n to be smaller to delta, so then 1 over 2n is smaller to delta. So given a delta greater to 0, we found x and x prime such that the difference is smaller to delta. So we have up to here. We now have to see the function. F of x minus f of x prime. Remember that we had defined f of x to be 1 over n. So this is f of x is 1 over n minus x prime was 1 over 2n. And then using the definition of our function, f of 1 over n is n, and f of 1 over 2n is 2n. So then this is n minus 2n is minus n, and as n is a positive number, this absolute value gives us n. N was a natural number, so it's always greater than or equal to 1. But we actually took 1 to be equal to epsilon. So then f of x minus f of x prime is greater to epsilon. Because we have here, we took the epsilon equal to 1, and this is exactly what we wanted to have. So then we found an epsilon equal to 1, such that for every delta greater to 0, there exists x equal to 1 over n and x prime equals to 1 over 2n, such that x minus x prime was smaller to delta, but f of x minus f of x prime was greater than or equal to epsilon. And then what this is telling us is that f of x, defined as 1 over x, is not uniformly continuous. So then, if f is continuous, it doesn't imply that f is uniformly continuous. So let's now try and see what this means graphically. 1 over x is something like this. This is just a sketch, so the drawing is awful, but it's enough for our needs. Let's say we take an epsilon here. For this epsilon, the values of our function are here and here, so this would be the delta we have to take. Now let's take another epsilon. Notice that for an epsilon that's a bit bigger than the previous one, the delta is huge. It's twice as much as the other one. But for now, we don't care much. Now let's say we take an epsilon here that's pretty big. One would expect the delta to be bigger because we took a small epsilon here and the delta was small. We took a bigger epsilon and the delta was bigger. But now for this epsilon, the delta has to be super small. And this is showing us, in this case, that the delta does depend on x and on epsilon. It always depends on epsilon. But in this case, it depends on x, because when we're close to 0, as our function is exploring towards infinity, the delta has to be dependent on that explosion, so it has to be dependent on x. And then functions like this that have this sort of asymptotes and explosions, these functions will not be uniformly continuous. But now when we look at the other function, x squared, we were in the interval 0, 1, that's why I'm not drawing the negative part, but it actually is the same. It's going to be uniformly continuous everywhere. Then when we take out an epsilon, we have this delta. When we take this other epsilon, we have a bigger delta. And let's just try one more time. We take this epsilon, and the delta is again, it's uniform throughout our function. We take bigger epsilon, we have a bigger delta. And it doesn't depend how close we are to 0, how far we are. It's uniform for every x. So let's finish now the video with a very, very important theorem. It's called the Heine-Cantor theorem, and it says that if a function f is continuous in the closed interval ab, so here ab is our interval a, then the function is uniformly continuous in the whole interval. Let's go ahead and prove it. And we're gonna do a proof by contradiction. So suppose that f is not uniformly continuous, then we have the definition for when f was not uniformly continuous. There exists, let's call it epsilon 0, a positive number such that for all delta greater to 0, there exist two numbers, x and x prime, in an interval that is, in this case, AB closed, that verify that x minus x prime in absolute value is smaller to delta, but the absolute value of f of x minus f of x prime is greater than or equal to epsilon 0. Now we have something for every delta greater to 0, and in particular all these things will be valid for delta to be 1 over n, where n is just a natural number. So we know that for this delta there will exist x and x prime, let's call it x sub n and x prime sub n, such that x of n minus x prime sub n is smaller to delta, that is smaller to 1 over n. And f of x sub n minus f of x sub n prime is greater than or equal to epsilon 0. So now we did this for one natural number, and we can continue taking other natural numbers. So doing this for every natural number n, we obtain a sequence x sub n and x sub n prime that satisfy that the difference is smaller to 1 over n, and that the difference of the f is greater than or equal to epsilon 0. Now, x of n is a sequence defined in a closed interval AB. So then x of n is bounded. And then we can use Weierstrass theorem and say that there exists a subsequence S sub n sub k that converges. That is, that the limit when k tends to infinity of x sub n sub k is equal to some number c. If you don't remember much about sequences, then I suggest you check out the videos we have made about this. So then we know that for every k, x of ends of k is between a and b. And then this tells us that our limit will be also between a and b. So we have two sequences, x of n that we know that a subsequence x of n sub k converges to c. But we have this other one. And what we're gonna do is we will prove that the limit when k tends to infinity of x sub nk prime, that is a subsequence of our second sequence, is also c. To do this, we want to calculate the difference x of n sub k prime minus c. This is the same as doing x of n sub k prime, and now subtracting x sub n sub k and adding it again. And now we can use the triangular inequality and write this as the absolute value of x of n sub k prime minus x of n sub k plus the absolute value of x of n sub k minus c. This is the same as writing the first term as x of n sub k minus x of n sub k prime. But now we can bound this, and because we know that these two numbers satisfy this yellow property, that is x of n minus x of n prime is smaller to 1 over n. And so x of nk minus x of nk prime will be smaller to 1 over n sub k. And we just leave this other term. So now if we make k big enough, then we can bound this with 1 over k plus what we had. So now what we're gonna do is give it a number, let's say rho greater to 0. We're going to let k1 be a natural number such that 1 over k1 is smaller to rho over 2. And now we let k2 be another natural number such that if k is greater to k2, then x of n sub k minus c is smaller to rho divided by 2. This k1 exists because rho is just a positive number, and k2 exists because we know that the limit of x of n sub k is c. So this is just using the definition of a limit. So then if we take k to be the maximum between k1 and k2, then both these two things will be true. And so we can rewrite the inequality we had, that is x of nk prime minus c smaller to 1 over k plus x nk minus c. But now when we take k to be greater than or equal to this maximum number, then 1 over k is smaller to rho over 2, and x of n sub k minus c is smaller to rho over 2, and this sums to rho. So what this is showing is that the limit when k tends to infinity of x sub n k prime is equal to C. And this is what we wanted to prove here. So far this proves nothing about our theorem, that is, that our function f is uniformly continuous. So, to sum up, what we have so far is we have two sequences in AB that both converge to this limit C that is also in AB. But now f is continuous. So what this tells us is that the limit when k tends to infinity of f of x sub n sub k, this is f evaluated in the limit, that is f in C, and also the limit when k tends to infinity of f in x of n k prime has to be f in C, because the limit of xn prime sub k is also C. So then the limit when k tends to infinity of x of x and k minus f in x and k prime, the limit of the sum is the sum of the limits, so this is f in C minus f in C, and this is 0. But this is an absurd. And this is due to, and I'm gonna write it like this, I'm gonna put the mark here on top. We had that the x and x prime that we could find satisfied that they were smaller to delta, the difference, but also that f of x minus f of x prime was greater to epsilon 0. And epsilon 0 was a positive number. And the numbers in our sequence x of n and x of nk, and therefore the numbers in the subsequences x of n sub k and x of n sub k prime, must also satisfy this condition. F of x sub n sub k minus f of x sub n sub k prime has to be greater than or equal to epsilon 0. So then it's an absurd because we have that it is 0, and the absurd comes from supposing that f is not uniformly continuous. So then f is uniformly continuous, and that proves our theorem.